Hello, my name is Khanh Bui. I'm a PhD student at the Arctic University of Norway. Today, I will be presenting my paper for the OMAE 2020 virtual conference. The title of the paper is A Decision Support Framework for Cost-Effective and Energy-Efficient Shipping. The second author of the paper is Dr. Prasad Pereira. This is the outline of my presentation. I will start off with background or research problem, followed by proposed decision support framework, research objectives, methodology, and then I will be talking about life cycle cost analysis, advanced data analytics for ship performance monitoring. Finally, I will finish up my presentation with conclusion. Background research problem. Air emissions from shipping are in the form of carbon dioxide, CO2, sulfur oxides, SOx, nitrogen oxides, NOx, PM, particulate matter, and so on. According to the third greenhouse gases study established by the International Maritime Organization, IMO, international shipping is responsible for 2.6% of global CO2 emissions, 12% of global SOx emissions, and 13% of global NOx emissions. As many of you know, CO2 contributes to global warming. SOx and NOx cause acid rain. SOx, NOx, and PM are harmful to human health. Regulations on reducing air emissions from shipping can be divided into three categories. In terms of air pollutants regulation, NOx, SOx, and PM emissions are addressed in Regulation 13 and 14 in MARPOL Annex 6, Chapter 3. The Global Sulfur Cap 2020 it just entered into force, limiting sulfur content in bunker fuel to 0.5%. In terms of greenhouse gases regulation or target, greenhouse gases emission are addressed in MARPOL Annex 6, Chapter 4 with two measures. EDI, Energy Efficiency Design Index for new vessels, SAM, Ship Energy Efficiency Management Plan for existing vessels. The IMO has established a target for global shipping to decarbonize by at least 50% by 2050 compared to 2008 levels. In terms of data-driven regulation, there are two regimes. IMO DCS, Data Collection System, and EU MRV, Monitoring, Reporting, and Verification. Given this strict regulation, the maritime industry is dealing with a decarbonization challenge. The challenge is uncertain since there is clearly no single route for decarbonized long-distance shipping. The challenge is also complex since there are many criteria such as environmental, technical, financial, practical, and social should be considered. Given the research problem, we propose a decision support framework for cost-effective and energy-efficient shipping. So let's dive into this framework. The proposed decision support framework consists of three parts. The first part is life cycle cost analysis. The middle part is data handling, mapping, and quality assurance, or data pre-processing. The final part is performance quantification, data post-processing. Various innovative technologies will be combined and be expected to achieve fuel efficiency and reduce emissions from ships. So in the first part, we will conduct life cycle cost analysis, LCCA, on three components. LCCA on bunker fuel, data from oil and gas field to fuel pump, LCCA on engine technology with higher combustion efficiency, data from materials to product disposal, and data from actual engine testing. LCCA on propeller technology, data from materials to product disposal. So the outcome of the LCCA will fit into the data pre-processing part, where type of vessel, technology combinations, and operational route will be selected. Wind, wave, and current effects related to operational profile can be also included under this part. After that, we will manage to obtain large-scale data for advanced data analytics framework. So we are looking into the engine propeller combinator diagram. The dark regions are data clusters that relate to specific operating modes for the selected ship engine. And from that, we will quantify ship performance in order to derive KPI with respect to propulsion power versus engine emissions, system installation, operational maintenance and disposal, costs versus benefits, and environmental impact. Research objectives. The proposed framework comprises the life cycle cost analysis and the advanced data analytics for ship performance monitoring. So the ultimate objective of the study would be a smart decision support tool for the achievement of cost-effective and energy-efficient shipping. Methodology. So it is transdisciplinary research, which is defined as interdisciplinarity in combination with participatory approach. The study across boundaries of academic disciplinary, nautical science, marine engineering, artificial intelligence and machine learning, and data science. The study also includes non-academic participants such as marine engine manufacturers, ship owners, and ship operators. Life cycle cost analysis. From a cradle to grave perspective, the overall life cycle cost (LCC) can be expressed as the sum of installation costs (CI) plus the sum of operation costs (CO) plus the sum of maintenance costs (CM) and the sum of end-of-life costs (CEOL). Looking into a cradle-to-grave perspective, there are several processes throughout the bunker fuel life cycle: extraction from fuel, transportation of raw material, fuel production, transportation of bunker fuel, and combustion. For the propeller technology, the propeller passed through several major processes during its lifespan, including purchase from manufacturer, propeller installation, maintenance in dry dock, and disposal. So the total life cycle cost can be derived from the total estimation of own costs associated with these processes. There are four major processes during an engine's life cycle. They are installation, operation, maintenance, and an applied process. Under the installation process, there are several activities are divided, such as purchase from manufacturer, transportation, fuel supply, engine installation, and electricity supply. Under operation process, several activities are divided, such as fuel supply, transportation, engine operation, lubricant oil supply, and transportation. The maintenance process consists of several maintenance activities, including purchase of spares, transportation, fuel supply, engine maintenance, and labor force. The end-of-life process includes several activities: engine disassembly, transportation, fuel supply, recycling and scrapping, and electricity supply. Advanced data analytics for ship performance monitoring. So, what is Advanced Data Analytics (ADA) for ship performance monitoring? Domain knowledge and digital modeling play important roles under ADA since they interact with a number of analytics layers such as descriptive analytics to identify data anomalies through two filters. Filter 1 due to missing data points, filter 2 due to sensor faults or system abnormal events. Diagnostic analytics to remove and recover data anomalies. Visual analytics to visualize the improved data and to identify the relationships among parameters. Predictive analytics to predict vessel operation behaviors, and decision analytics to derive KPI with respect to propulsion power and engine emissions towards achieving energy efficiency and reducing emissions. The ADA is proposed to overcome one of big data challenges, data veracity, which is related to the quality of data. And as you can see, there are some facts about the data veracity problem. Digital modeling. Kernel density estimation (KDE) is used in digital modeling. The upper figure shows the difference between a bivariate histogram and a kernel density estimation. So basically, KDE is constructed from Gaussian distributed plot from every data point, and then we sum them up. The lower figure shows a data generated from a combination of two bivariate normal distributions visualized through a scatter plot, a histogram, a true density, and a kernel density estimation. Apart from that, we also use a clustering technique based on probability density estimation using Gaussian mixture models and a procedure called expectation maximization (EM) for distributing data into different clusters. Ship performance and navigation data. We managed to obtain a ship performance and navigation data set from a real bulk carrier. There are 12 parameters in this dataset: auxiliary fuel consumption, main engine fuel consumption, auxiliary power, main engine power, shaft speed, relative wind speed, relative wind direction, GPS heading, speed over ground, speed through water, trim, and average draft. With the domain knowledge, we define the maximum and minimum values to filter out data anomalies through filter 1 under descriptive analytics. Engine data clustering. Using kernel density estimation (KDE) and Gaussian mixture models with EM algorithm for two engine parameters, engine power, shaft speed, we found that the data are grouped into three clusters: cluster A1, cluster A2, and cluster A3, meaning that the selected ships operated in three specific engine modes. After that, the data cluster A1 was selected to proceed our investigation. We will look into the trim and draft condition of this data cluster. So we found that there are two subclusters, data cluster A11 and data cluster A12, with respect to trim and draft condition of this data cluster. Let's talk about visual analytics. We chose the data cluster A12 in pink color for the purpose of illustration. We were investigating the structure of this cluster, and it is demonstrated by a set of singular vectors. In this case, a 12-dimensional singular vector space, as you can see from the figure on the right-hand side. So the singular vectors are dotted circles in descending order from the outermost circle to the innermost one. A colored circle in each dotted circle expresses the relative correlation among the parameters. The side of each colored circle represents the significance of the parameter correlation. The color bar shows the high positive correlation in red and high negative correlation in blue. So the whole idea for visual analytics is to identify the relationships or correlations among parameters in a high-dimensional space. Let's take a look at the top singular vector. There is an increase in the shaft speed, so the main engine power also increases. For the second singular vector, a decrease in the main engine power leads to a decrease in the main engine fuel consumption. This is due to trim adjustment by the vessel operator for achieving energy efficiency. There is also a decrease in the relative wind direction and the relative wind speed in this condition. For the third singular vector, a decrease in the ship speed leads to a considerable decrease in the relative wind direction. For the fourth and the fifth singular vectors, a decrease in the auxiliary power results in a decrease in the auxiliary fuel consumption. For the sixth singular vector, a significant increase in the speed of ground leads to a decrease in the relative wind direction. For the seventh and the eighth singular vectors, the correlation among parameters are not clearly observed due to data anomalies. Bottom singular vectors that have low singular values, there is no realistic correlations among parameters. Conclusion. A proposed decision support framework which comprises the LCCA analysis and the ADA for ship performance monitoring will play a pivotal role for decision-making processes towards cost-effective and energy-efficient shipping. In the first place, the LCCA discusses the potential processes and associated costs during the lifespan of the selected technologies. thereby providing the overview of the LCCA for the cost performance appraisal of these technologies. In the second place, the ADA for ship performance monitoring uses insight into digital modeling, visual analytics that can be used to overcome big data challenges. Such approaches can also provide better decision support with respect to increased energy efficiency. Future work for the LCCA will focus on total life cycle cost estimation of the proposed technologies in order to evaluate the long-term cost effectiveness. For the ADA, we will address the data veracity challenge by proper techniques. Thank you so much for your attention.